This video is a review of the EcoSmart 800 lumen LED light bulb. This one's coming from a company called Lighting Science. I think EcoSmart's a house brand for the Home Depot. We're going to take a look at this bulb, see how it performs, and we'll compare it against some of its peers, and then we'll tear it down and look at the engineering inside. Alright, the bulb's plugged into a kilowatt meter, which basically measures watts. One of the big advantages of LED bulbs, of course, is they don't draw much power. This kilowatt's indicating it's drawing about 13.7 watts, and the power factor is almost unity, so that's good. The wattage rating, however, on the package it says 13 watts, and this meter here is actually recording 13.6. One would think one should round it up to 14. In terms of power and power factor correction, the Cree bulb remains the best in this regard at 9.9 measured watts. The next best bulb, it was a Philips bulb at 12.7 watts. Now the bulb we're looking at today, the Eco bulb, is coming in at 13.7 watts. And the switch bulb is the worst at 13.5 watts. Okay, this is the flicker test. Some people are very sensitive to these light bulbs. They can produce flicker if they don't have adequate filtering capacitors on their output stage. A very simple setup to gauge how this bulb compares to other bulbs. Obviously a solar cell here which generates electricity proportional to the light that falls on it. The bulb, of course, in a socket that'll be fixed. Basically I'll turn the bulb on. And then on the oscilloscope here, of course, it produces a waveform. It's usually around 120 hertz. And measure the volts peak to peak, and then do that for each subsequent bulb. And from that, get a sense of how the flicker varies. Now, one thing that'll also happen here, I'll turn all the lights off, so there's only one light on during the test, so everything is nominalized. In terms of flicker, the voltage output from the solar cell and the Philips was the lowest, almost no perceptible flicker. We'll just normalize the output of the voltage from the solar cell to be to unity. The next best one was the Cree bulb here, followed by the bulb we're looking at today, the EcoSmart, and then quite dramatic flicker coming out of the switch bulb. In this test, we'll mate the light bulb with obviously a light dimmer. One problem with a lot of LED bulbs, they actually call it very special dimmers, and quite some complications there. And some bulbs which claim to be dimmable, quite frankly, not so good. So this is probably the cheapest dimmer one could find. I don't know how old it is. It certainly isn't rated for any LED light bulbs. But since I'm sure a lot of customers don't really want to be replacing their dimmers when they buy a bulb, let's see how this one performs. This is actually really quite excellent. A lot of LED light bulbs want to snap on at low voltages, but this one's got a really smooth motion to it, so the dimmability of this bulb appears to be excellent. In this part of the video, we'll take a look at how light comes out of the bulb. The old traditional incandescent light bulb was pretty good. It was pretty consistent around the radius of the bulb, basically the same amount of luminous flux. Now, LEDs, of course, are extremely directional and very small point sources, so one of the real challenges in optical engineering is to produce a bulb that has light coming out in a satisfying way. Now, on the first look of the bulb, it looks like it's perhaps more of a side emitter than it is a down emitter. So one way of finding that out is actually quite easy, a bit of amateur science. You can purchase a light meter for well under $20 and run it around at a constant radius from the center of the bulb. Record the numbers on a polar graph, and then you can draw a graph, and you get a good sense pretty quickly actually of how the light comes out of the bulb. So I'll do that. I'll get the line onto this polar graph and have a little discussion as to what the bulb looks like. Okay, so here's the polar graph. The black line is the lux along various angles. Lux, of course, being the lumens per square meter. And you can see sort of a bulge here and a bulge here, and it's a little bit less down here. And of course, it drops off dramatically as you get towards the base here, where there's more metal than there is light. So again, right, this is showing that this bulb is well suited to, say, a desk lamp fixture, but a fixture, well, say, like, for example, like this here, where it wants to point downwards mostly, is an area where this bulb isn't quite as strong as it would be, say, in a traditional lamp. So it's one of those things you have to sort of pay attention to when you're buying LED bulbs. they're actually now becoming fixture specific. Let's crack the bulb open and see what's inside it. Before we do that though, let's just externally look at the shell here. It's polycarbonate, sort of a plastic diffuser on the LEDs. A really large heatsink on the product. Probably a retention ring that's used to retain the electronics, and then of course the A-ball base. Okay, so the top's obviously off the diffuser. It's not a side emitter, it's actually, you can see all the LEDs are planar on this aluminum backed circuit board pointing downwards. And this little top here actually has a little white light diffuser, which of course causes the light to be bounced, so it comes out the sides a little bit, and of course it does pass a bit through. Even this piece is actually fairly complicated. You can see that this little white disc will not come out because we have two pieces of plastic which actually have been ultrasonically welded with this in the top. So this is just a really good indication of how complicated the optics get in these lamps. I'm trying to get these really bright point sources of light to diffuse evenly and attractively. Now, whilst we're looking down on the circuit board here, we can see there's 11 LEDs. And you can see these two little hand-soldered wires are connections down to what will be the AC to DC converter somewhere in the base of the bulb. So let's take this rivet off and continue the teardown. So the bulb's now, of course, in all of its constituent pieces. Light diffuser here, the circuit board which contains the 11 LEDs here. Clearly it's stamped out of a sheet of metal. The casting looks like aluminum, and it's probably been powder coated. A little retention ring which holds the circuit board on. Of course, the AC to DC converter. This will take a much deeper look in a second. The gray material is known as potting compound. It's poured around electronics and then sets into sort of a firm consistency. It's got a couple advantages. It allows heat to be sort of evenly drawn away from the surface electronics onto the outer area. Thermal gradients can really kill electronics reliability. Also provides a ability to create a very reliable assembly because you sort of lock everything in place. And then of course the Edison A base. Okay, an AC to DC converter circuit. All LED bulbs need this. Electric systems around the world are hundreds of volts of AC, and of course LEDs only need a couple volts of DC to work correctly. So yeah, all of these bulbs will have this kind of circuit board in them. What does vary though is the implementational details. Let's see, coming from on this side here, this item here is a fuse, for safety reasons of course. These two black cylinders are inductors, and there's some capacitors here as well. These are forming a EMI filter. What happens is you get a lot of energy being generated by these circuits, and you don't want to push that back into the electrical line because you can create all sorts of noise in the electrical lines and cause interference with other communication systems. The blue item here, of course, is a DC smoothing capacitor. This is a switching regulator. We'll just flip it over here. I'm sure we'll find, yeah, so we'll find a controller here. We'll find a full wave rectifier here. This is a MOSFET, which is the switching transistor. The slot cut here is for isolation purposes. Circuit boards have, although they're not in conductors, if you want to make really great isolation, you cut a hole in your circuit board. It's good practice. It's, I think it's probably only halfway rectified on this side though. This is what causes the flicker in a bulb. If this filtering capacitor and filtering circuit isn't done really well, you get a lot of AC components and there will also flicker. This is also one of the items that has a failure mechanism. Rubicon, 50 volts, 330 microfarads, 130 volts. So an appropriate capacitor for the application. We can read, of course, indeed, confirmation it was designed by Lighting Sciences, not a third party that we see sometimes with designs. The standard placement fiducial, so the circuit board can be picked in place by a machine. Let's see, here's the PCB Rev F. Let's see, they took 6 tries to get the circuit board right. What is interesting though is actually it's quite a large circuit board, and circuit board material is actually quite expensive. For example, the switch bulb, which unfortunately is in 2 pieces, but I'll put it back together here. There's the switchboard. You can see how much smaller it is. That's interesting actually. Circuit board material is sold on a per square inch basis, and you're probably looking at least maybe 5 or 6 cents of circuit board material that didn't need to spend, or at least clearly like switchwood, you can go buy more compact. Even actually the most economically challenged bulb that I tore down previously from GE, another really straightforward design with not a lot of super clever engineering going on. It has a circuit board which is actually smaller, so a little bit of surprise. Fairly large circuit board for the bulbs I've torn down to date. Alright, well, that was fun. So that was the review, comparison, and extreme teardown of an EcoSmart 800 lumen LED light bulb.